last time we were talking about, we were just sort of reviewing random variables. So today we're going to talk about, what we're going to do is we're going to introduce the hardware model for digital communications. So this will be the model that we keep in mind when we discuss the mathematical aspects of this course. This will be the hardware that's motivating us. So what we're going to do is we're going to talk a bit about the hardware. Once I introduce to you all of the pieces that go into that model, we will see that in one of those pieces, in fact in the receiver amplifier, is the most critical aspect of the digital communications problem, which is noise. So noise is introduced as a natural feature of the amplifier. And it's not, it's not deliberate, it's not something, in fact it's not even something you can design against unless you can somehow cool the amplifier to absolute zero. Noise is always present. So to finish off today, we'll start talking about the theoretical foundation of what noise is. It's basically a Gaussian random process. We'll talk a little bit about random processes. Okay, digital communications hardware model. So fundamentally, at the highest level, at the highest black box level, this is what we have. We have some message source. Which connects to a transmitter. The transmitter sends its transmissions over a medium. Medium is observed by a receiver. And finally, the receiver reports the message it detects out of the medium to a message sink. So data flows here, flows from the message source through all of this hardware to the message sink. So we're most concerned with the transmitter and the receiver, but let's talk about each of these boxes in turn. So the message source basically this is the information you want to send. So this can be any form of information. Now it can't be just any form because this is a data communications class. The information coming out of the message source must be expressed digitally. So it's any form of information expressed digitally. But fortunately, anything that we want to send, there is likely a digital representation for it. So for example, we can send text, like emails. Send executables. So these are forms of information that are naturally digital, that are naturally discrete in nature. We can send images. Now images are normally continuous valued and not necessarily digital, but there's lots of ways to encode them, like JPEG. So on, just as long as you have some digital encoding for that. Audio, again, lots of encodings, MP3, AAC, so on. Video, lots of encodings for that. MPEG-2, things like that. Generally in this course, we will not discuss the message source. But basically, as long as you can take information and express it digitally. So by digitally, what I mean is expressed as a vector of discrete elements. So in other words, anytime you can take information and express it as a vector of discrete elements, you can then transform it into binary, and then you can transmit it using the techniques that we're going to talk about. Towards the very end of the course, we will talk a little bit, if we have time, we will talk a little bit about data compression. And that's a message source technology. But generally, we're not worried in this course about where the information comes from. By the time it gets to us, it's already binary. It's already expressed digitally. And all we have to do is send the digital symbols across the medium. Okay, the next box, the transmitter. So this is hardware to convert digital information into a transmittable waveform. So this is one of the two things that we're designing here. The two things we're designing here are the transmitter and the receiver. So what's input to the transmitter is a sequence of digital symbols. So let's, for the sake of argument, call them binary bits. So there'll be a sequence of zeros and ones here, and the transmitter's job is to transform those into a waveform that can be sent across the medium. So we're gonna see some examples of that in a minute. But the kind of things that you have in mind are basically we're transforming this vector of bits into a real valued function. So for example, one very simple one would be, let's say I have 1010 or something. And what we're going to do is we're going to send that as, we're going to send a 1 as an amplitude plus 1 for time t. We're going to send a 0 as an amplitude 0 for an additional time t. So this would be a very simple modulation scheme. This is actually called on-off keying. And that is what that would look like as a taking this binary vector and transforming it into a real value function to be sent across the medium. So unfortunately, this particular real value function might not be suitable for all types of medium. So design criteria that the transmitter has to cope with include, so the transmitter needs to cope with medium characteristics such as bandwidth. Bandwidth is something we're going to talk a little bit about much later in the course. Does anybody have an idea of what bandwidth is? It's basically the size of, if you take the Fourier transform of a signal, the bandwidth of that signal is basically its extent in the Fourier transform, so how wide it is in frequency. And it turns out that many media have restrictions on what you can do. So for example, sending something over a telephone line, there cannot be a DC component for one thing. So there's no, you can't send a signal that has a Fourier transform component at 0 or greater than 0. And for another thing, the width of that signal in the frequency domain can't be any greater than about 4 kilohertz. So it turns out that imposes stringent requirements that we will talk about later. The medium.